Hi everyone. Today in this video we will discuss about the remaining topics of the chapter oscillations. Okay. So here we will discuss about first of all what is meant by oscillations due to a spring. So here you can see in the diagram a spring is fixed on a rigid wall and at the one end of the spring we are connecting an object of mass m. And if we stretch the spring by exerting force on the mass m, we can see that, and once it is released, we can see that the spring will start executing oscillations. Okay, and here we are going to discuss that those oscillations due to that spring can be considered as simple harmonic motion. Okay, so here x equal to 0, that is the mean position, and it moves between plus a and minus a, and the force constant of the spring is k, and what is a? A is the maximum amplitude and m is the mass of the object. So x equal to 0 means that is the position at which the spring is in equilibrium. Not spring, it is spring. Okay, so consider a block. If it is pulled on one side and is released, and then it executes to and fro motion, that already we discussed about a mean position, or in other words we can say that it executes simple harmonic motion. So we can write f of x equal to minus kx. In the case of spring, that already we discussed in the chapter work, energy and power, that is the restoring force acting on the spring is given by minus k into x. And what is k? K is known as spring constant or force constant, and x is the displacement. So k is known as spring constant or force constant. So we can write by using Newton's second law of motion, we can write f is equal to ma. So m into d square x by dt square. Okay, dt2, it is not that, it is d square x by dt square. So m into d square x by dt square can be written as minus kx. No, by using Newton's second law we can write f is equal to ma, and here restoring force is given by minus kx. So we can equate both. So we are writing ma is equal to minus kx, or we can write m into d square x by dt square equal to minus kx, or we can write it as d square x by dt square plus k by m into x equal to 0. Okay, it is equal to 0 that we have to write. Okay, by mistake it is not written. So d square x by dt square plus k by m into x equal to 0, or we can write d square x by dt square plus omega square into x equal to 0. That is the differential form or differential equation for simple harmonic motion. So if you compare it with this equation, we can write omega square equal to k by m, or omega angular frequency can be written as root of k by m. No. So if you know the omega value of omega, you can find time period. What is the relation between omega and t? Omega is equal to 2 pi by t. So we can write time period is equal to 2 pi into root of m by k. And what is t? T stands for time period. M is the mass of the object which is connected to the spring, and k is the spring constant. Okay, so here you can see that the oscillations produced by a spring can be considered as simple harmonic. So how you have to show? You have to write, you have to get that relation d square x by dt square plus k by m into x equal to 0. And you have to write that this can be considered, or this is similar to the differential form of simple harmonic equation, which is given by d square x by dt square plus omega square x equal to 0. Like that you have to write, and from that you have to find the expression for the time period. Okay. And next we will discuss about if the springs are connected in series, how to find the expression. Okay, so here on the right hand side you can see that two springs having spring constants k1 and k2, they are connected to a mass. Okay, so they are connected in series. So this type of combination is known as series combination. So let x1 and x2 be the extension. Okay, the extension produced on each spring, let it be x1 and x2. And here same restoring force is acting. No, restoring force acting is same. So we can write f is equal to minus k1 x1, which is equal to minus k2 x2. So we can write x1 can be written as, how we can write x1 is equal to minus f by k1, Same way x2 is equal to minus f by k2. So x1 is the displacement in the first spring, extension produced in the first spring, and x2 is the extension produced in the second spring. So total extension we can write it as x equal to x1 plus x2, which can be written as x1 and x2 you can substitute minus f by k1 minus f by k2. Minus f can be taken common into 1 by k1 plus 1 by k2. If you simplify, what you will get by taking LCM, k2 plus k1 by k1 k2, or f is equal to minus of k1 k2 by k1 plus k2 into x. So if you replace these two springs with a single spring having force constant ks, what we can write, f is equal to minus ks into x. So if two springs are connected in series, the effective spring constant is given by k1 k2 by k1 plus k2. Okay, so this relation is very important. So if two springs are connected in series, effective spring constant is given by k1 k2 by k1 plus k2. Time period, accordingly you can find time period is equal to 2 pi into root of m by k. By using that, instead of k you have to substitute it as k1 k2 by k1 plus k2. Okay, this is the case of series connection. Now we can see if the springs are connected in parallel like this. So k1 and k2 are the spring constants, and here the extension produced will be same. No, extension produced on each spring will be same. So let it be y. So f1 is equal to minus k1y and f2 is equal to minus k2y. So total force can be written as f1 plus f2. So minus of k1 plus k2 into y. So instead of these two springs, if we are replacing it with a single spring having, in that case also, if the extension is y itself, we can write f is equal to minus kp into y. What is kp? Kp stands for the parallel effective spring constant in parallel connection or parallel case, that is given by k1 plus k2. Okay, is it clear? So if two springs are connected in series and in parallel, what is the effective spring constant, that you can write. Accordingly you can find frequency. Time period you can find its reciprocal, you can find it as frequency also. Okay, that they substituted and find out. Time period is given by 2 pi into root of m by k, or frequency is 1 by time period. So frequency can be written as 1 by 2 pi into root of kp by m. What is kp? Kp stands for effective spring constant in parallel connection. Okay, now we are considering vertical oscillations of the spring. If the spring is connected, or if the spring is kept vertically, what will happen? Okay, so this is the first case. There is no mass is connected. In the first diagram, no mass itself, it is not connected. Next case, what we are doing, we are connecting a mass m. So what happens, that time itself some displacement will be there, so that we are writing it as d. So at equilibrium condition we can write mg is equal to kd. No, why? Because mg is the force acting downwards and kd is the restoring force. So we can write at equilibrium mg is equal to kd, where kd is the initial displacement. Okay, now if the body be pulled vertically downwards through a small distance x from its equilibrium position and then released, what happens? It begins to oscillate up and down. Okay, so here in that case, what is the restoring force? Restoring force we have to find. No, resultant force we have to find, that is given by mg is acting vertically downwards. What is the force acting on upwards? That can be written as minus k into d plus x, because now from the equilibrium position, what is the displacement? Net displacement is given by d plus x. No, so mg minus k into d plus x, and we know that mg is equal to kd. So what you got here, also you got net force as minus kx, because kd and kd got cancelled. So again we can find m into d square x by dt square equal to minus kx. So d square x by dt square equal to minus k by m into x, or we can write it as d square x by dt square equal to minus omega square x. That is a differential form of simple harmonic motion. So omega square equal to k by m, or time period is equal to 2 pi into root of m by k. So here you can see that this is one important result. If the oscillation is horizontal or vertical, it doesn't matter, the time period remains same. If the mass connected to that object is same and if spring constant remains same, if the same spring is connected to the same mass, if the oscillations are vertical or horizontal, doesn't matter, time period remains same. Now we'll discuss one or two problems related to this. So first problem, a spring compressed by 0.2 meter develops a restoring force of 25 Newton. A body of mass 5 kg is placed over it. Okay, it is compressed by 0.2 meter, develops a restoring force of 25 Newton. A body of mass 5 kg is placed over it. Deduce force constant of the spring, depression of the spring under the weight of the body and the period of oscillation if the body is disturbed. And it is given that you can take the value of G as 10 meter per second square or 10 Newton per kg. Displacement Y is given 0.2 meter, F is given 25 Newton. So force constant we can write K is equal to F by Y. F is equal to Ky or Kx. No. So 25 by 0.2 which is equal to 125 Newton per meter. And force is given, what is mass is given 5 kilograms. So force can be written as 5 kilogram weight, no, mg. Mass into acceleration due to gravity. So 5 into 10 which is equal to 50 Newton. Now in that case displacement we can write F by K. So 50 divided by 125, 0.4 meter, and time period we can find 2 pi into root of m by K. So mass is given, spring constant is given. By using that we can find time period which is equal to 2 pi by 5 seconds. Okay. Now we'll discuss another problem. A 0.2 kilogram of mass hangs at the end of a spring. When 0.02 kilogram more mass is added to the end of the spring, it stretches 7 centimeter more. If the 0.02 kilogram mass is removed, what will be the period of vibration of the system? Okay. So what it is given, by adding 0.02 kilogram mass, the spring stretches by 7 centimeters. So we can write mg is equal to kx. No. Okay. Or by using that we can find the spring constant K is equal to mg by x. So 0.02 into g value we are taking it as 10 by 7 into 10 raised to minus 2, 7 centimeter. So 20 by 7 Newton per meter. Now when 0.02 kilogram mass is removed, period of vibration we can find, time period is equal to 2 pi into root of m by k. 2 pi into root of 0.2 divided by 20 by 7. Okay. If the mass is removed, initial mass is 0.2 only, no. So 2 pi into root of 7 by 100. If you simplify, you will get it as 1.66 seconds. Okay. Now we will discuss about the oscillations due to a simple pendulum. This also can be considered as simple harmonic. So for that we are considering a simple pendulum. Let m is the mass of the bob and L is the length of the pendulum. And here when the pendulum bob is at some position, we can see that which are the forces acting. Tension is acting along the thread to the point of support. Mg is acting vertically downwards, and if you resolve Mg into components and if theta is the angle made, you can see that Mg cos theta is balanced by tension and Mg sin theta is acting towards the main position. So we can say that Mg sin theta is the restoring force which tries to bring the pendulum bob to bring it back to its original position. No. So what we can write, the restoring force can be written as minus mg sin theta. Why we are writing minus sign? To show that it is acting towards the main position or it is acting opposite to the direction of displacement. And for small angles we can write sin theta can be approximately equal to theta. No. So we can write restoring force equal to minus mg into theta. And what is theta? Angle can be written as, for small angles, angle is equal to arc length by radius. And what is arc length? Arc length is the displacement of the bob. No. So we can write it as minus mg into x by L. arc length by radius. Arc length stands for the displacement and radius equal to length of the pendulum. So we can write it as minus mg into x by L. Now we know that by using Newton's second law we can write force equal to mass into acceleration, which is equal to minus mg into x by L. Again, instead of acceleration we can write second derivative of displacement. So we can write m into d square x by dt square equal to minus mg into x by L. M can be cancelled. What you will get, d square x by dt square equal to minus gx by L, or we can write d square x by dt square plus gx by L equal to 0. This is similar to our simple harmonic motion equation of differential form. No, d square x by dt square plus omega square x equal to 0. This is the differential form of simple harmonic motion. So if you compare both, what you can write? You can write omega square equal to g by L. No, omega square equal to g by L, or omega is equal to root of g by L. And if you know omega, you can find the time period. Time period is given by 2 pi by omega, which is equal to 2 pi into root of L by g, and that is the time period of simple pendulum. Okay, and is it clear? So this derivation that is show that the oscillations of a simple pendulum is simple harmonic, and hence obtain an expression for the time period like that normally it is asked. So directly you will get. So for all those cases, what you have to do, anything if it is asked to show that it is simple harmonic, you have to get the expression for the restoring force, and you have to obtain in such a way that that differential equation you have to get in that, you have to modify it into that differential equation form, and by comparing it with both you can find the expression for angular frequency. Okay, this is the way to find any oscillation to show that simple harmonic motion. Okay, so the expression for time period is given by 2 pi into root of L by g. What is L? L stands for the length of the pendulum, g is acceleration due to gravity at the place, and t is the time period. Okay, now we'll discuss one problem. What is the length of a simple pendulum which ticks seconds? Okay, so the length of a simple pendulum which ticks seconds means whose time period is 2 seconds. A pendulum which is having time period 2 seconds is known as which ticks seconds. Okay, so time period is given 2 seconds. Acceleration due to gravity, if it is not mentioned, you can take it as 9.8 meter per second square. By using that, you can find time period is given by 2 pi into root of L by g, or L is equal to t square g by 4 pi square. All data is given. Time period is given 2 square into 9.8 divided by 4 into pi square, value is 9.87. So if you simplify, you will get it as 0.992 meters. So that is the length of the pendulum which is having time period 2 seconds. So it will not be given directly, so they may give it as which ticks seconds, means which is having time period 2 seconds. Okay, now we will discuss about free oscillations. So from this diagram itself you might have got an idea what is meant by free oscillations, or it is also known as undamped oscillation. If a body capable of oscillation is slightly displaced from its position of equilibrium and left to itself, it starts oscillating with a frequency of its own. Such oscillations are called free oscillations. Okay, once just we are vibrating, we are displacing that object from its position. After that we are not exerting any force. Then once it is displaced from its equilibrium position, what happens? It starts oscillating from its own, with its own natural frequency, and that type of oscillations are known as free oscillations. It is also known as undamped oscillations. Okay, so here one of the important property of these free oscillations, you can see that amplitude remains same. Okay, is it clear? Amplitude of the oscillations remains same. Now what happens? Now we are going to discuss about damped oscillation. So these undamped oscillations or free oscillations, it happens, but what happens? Amplitude will not remain same. Amplitude gradually decreases. In the case of pendulum itself, if you are allowing to oscillate that pendulum, once you are exerting force and once after that if you release, what happens? It will oscillate, but after some time it comes to rest. No, why? because of air resistance, or if it is oscillating in a fluid, if it is oscillating in a liquid, viscosity will be there. So some energy will be utilized to overcome those dissipative forces, because of which what happens? The energy of the oscillation or oscillating object gradually decreases, and hence the amplitude of oscillation also gradually decreases. That type of oscillations are known as damped oscillations. Okay. The oscillations in which the amplitude decreases gradually with the passage of time are called damped oscillations. So undamped oscillations are only theoretical. Practically all oscillations are damped. Why? Because air will be there, air resistance will be there. Otherwise, if we are conducting in a liquid medium, viscosity will be there. To overcome all those dissipative forces, some of the energy of the oscillating object will be used, and hence the amplitude will not remain constant like free oscillations or undamped oscillations. Okay. Now we are going to discuss about maintained oscillations. So what is meant by maintained oscillations? If to an oscillating system, energy is continuously supplied from outside at the same rate at which energy is lost by it. Already I told you, in the case of damped oscillations, there will be dissipating forces will be there, because of which always energy loss will be there. So from outside we are continuously providing energy, because of which what happens? Amplitude will remain same. Such oscillations are called maintained oscillations. Okay. So amplitude will remain same. Okay. By how it remains same? To overcome the dissipative forces, or to overcome the energy loss by the dissipative forces from outside, somehow we are providing energy. So that the amplitude remains same. Such a type of oscillations are known as maintained oscillations. Examples, various examples are there. A child's swing in which energy is continuously fed to maintain constant amplitude. How? If a person is pushing the child's swing, with the same energy is continuously giving, so that amplitude of the swing will remain same. Another example is an electrically maintained tuning fork. Okay, tuning fork without exerting any, it will be maintained by electricity. And third one, the oscillations of the balance wheel of a watch in which the main spring provides the required energy. So all those are examples of maintained oscillations. So in that all those cases amplitude remains same. Okay. Now we will discuss about forced oscillations. So from the term itself you might have got an idea what is meant by forced oscillations. So when a body oscillates under the influence of an external periodic force, not with its own natural frequency, but with the frequency of the external periodic force, its oscillations are said to be forced oscillations. So what is meant by forced oscillation? A body is oscillating. How it is oscillating? It is oscillating with the help of external some periodic force. That is, that force is acting continuously at a regular intervals of time, and because of which it is not oscillating with its own natural frequency. Every system has its own natural frequency, okay, with which it can be oscillated. Once it is displaced from the equilibrium position, that object will start displacing. So all objects are having its own natural frequency. But what happens here in the case of forced oscillation, the system or object is not oscillating with its own natural frequency, but it is oscillating under, because of a periodic force it is oscillating, so it will oscillate with the frequency of that periodic force. Okay. So when a body oscillates under the influence of an external periodic force, not with its own natural frequency, but with the, this is very important, but with the frequency of the external periodic force. So the system is not oscillating with its own natural frequency. Why? Because that force is acting at regular intervals of time. No, so the system cannot oscillate with its own natural frequency. So it is oscillating with the frequency of the external periodic force. And such type of oscillations are called as forced oscillations. Okay. Examples. When a child in a garden swings periodically, presses his feet against the ground. You might have seen, no? A child who is in a swing, but periodically he or she will press the feet against the ground, no, or some other person continuously pushing by exerting force. So here what happens, it will not that but instead of oscillating with its own natural frequency by exerting force, it is moving. So this is an example of forced oscillations, okay, to maintain the oscillation. Another example, when the free end of the string of a simple pendulum is held in hand and the simple pendulum is made to oscillate by giving jerks by the hand. Okay, so by giving the jerks you can allow the pendulum to oscillate. So that is also forced oscillation, because here frequency is same as that of the periodic force exerted by the hand. Okay. Now the last topic that we are going to discuss is resonant oscillations and resonance. What is meant by resonance? I told you each system is having its own natural frequency with which it can be oscillated. And but some external driving force we are applying, periodic force we are applying, and if we are changing the frequency of the periodic force, we can see that when the frequency, natural frequency is matching with the frequency of the driving frequency, okay, when the driving frequency is matching with the natural frequency, that is when the angular frequency or when the frequency of driving force equal to the natural frequency of the system, amplitude will be maximum. So here you can see that in this graph also the frequency, we are varying the frequency of the driving force. So when the driving force frequency is equal to the frequency of the system, whichever may be the system, okay, so that case we can see that amplitude will be maximum. Okay, so amplitude maximum will be occurring for a forced oscillation. What happens when the natural frequency is matching with the driving frequency? Okay, that condition is known as resonance. Okay, so it is a particular case of forced oscillation in which the frequency of the driving force, this is very important, frequency of the driving force is equal to natural frequency. When the frequency of the driving force, okay, driving force has particular frequency and each system will have its own natural frequency. When both these frequencies are matching, when both the frequencies will be equal, what happens? The frequency of the driving force equal to the natural frequency of the oscillator itself, the amplitude of oscillations is very large. In that case, what happens? Amplitude will be large. That oscillation, those type of oscillations are called resonant oscillations, and that phenomenon is called resonance. Okay, these type of oscillations are known as resonant oscillations, and this phenomenon in which the frequency of the driving force is matching with the frequency of the system, okay, natural frequency of the oscillator, because of which amplitude becomes maximum, and that phenomenon is known as resonance. Okay, this resonance plays an important role in the case of tuning radio. When you are tuning a radio, what happens is that each station will be sending waves at a particular frequency. When you are tuning the radio, you are adjusting the value of the capacitance to make that frequency equal to frequency of that particular station. When it matches, what happens? You can hear that particular station. Okay, this is what happens. So resonance plays an important role in tuning radio, that we will discuss in next year. We will study about resonance once again. So at that time you should know what is meant by resonance. Okay, what is basically meant by resonance. Okay, so amplitude will be maximum. When amplitude will be maximum? When the frequency of the driving force matching with the natural frequency of the system. That case, those type of oscillations are known as resonant oscillations, and that phenomenon is known as resonance. And another example is that during march past, when the soldiers are doing march past through a bridge, if they are moving through a bridge, normally they will say to move out of steps. What happens is that if they are moving through the bridge by doing march past, what happens? Sometimes if their frequency is matching with the frequency of the bridge, chance is that that bridge may collapse. Once it happened also. So that is also, to avoid that one, normally they used to say to move out of steps through when they are moving through a bridge. Okay, is it clear? So this is about resonant oscillations and resonance. So this is also very important. What is meant by resonance? Initially all those derivations, various terms were there. Now it is not there. That's why we are not going to discuss. We are just to discuss what is meant by resonant oscillations and resonance. I hope all of you understood whatever topics that we discussed today. So that chapter oscillations also completed, and if you are having any doubt, you can communicate that to me. Thank you.